Several manufacturers produce 2-pole 60-amp, 230-volt EQP breakers that exhibit time current curves comparable to time delay fuses. These breakers offer inverse time delays, providing protection against both overloads and short circuits, much like time delay fuses. They offer protection from thermal overloads, fast tripping during short circuits, and accurate current limiting. Furthermore, these breakers ensure reliable operation even in demanding applications. Let's explore some prominent manufacturers and their series. Siemens offers the Centron 3RV20 series. Eaton provides the BR series. ABB features the System Pro EMAX series. Schneider Electric offers the Masterpact MTZ series. GE manufactures the IntelliGuard EQS series. Square D provides the QO series. The time current curves of these breakers are designed to mimic Type T or Type D fuse curves. This design provides high protection for sensitive equipment during short bursts of high current, such as those experienced during motor starting. They also facilitate coordinated protection with other upstream devices and minimize nuisance tripping caused by typical load fluctuations. These breakers find applications in various industrial and commercial settings where reliable protection is paramount. Examples include motor circuits, lighting circuits, power distribution panels, and switchboards. When selecting a breaker, it is very important to consult the manufacturer's specifications and collaborate with an electrical professional. This ensures that you choose the specific breaker model and protection characteristics best suited for your application. The core function of these breakers lies in their ability to provide robust electrical protection. They are designed to interrupt the flow of current when it exceeds a predetermined threshold, safeguarding equipment and preventing electrical hazards. The inverse time delay characteristic is crucial. It means that the breaker's tripping time decreases as the overcurrent increases. Small overloads, which may be temporary, are tolerated for a longer duration. Large overcurrents, indicating a more serious fault, trigger a rapid trip. This behavior is analogous to that of a time delay fuse, which also allows brief overcurrents to pass without blowing. When selecting a circuit breaker with time delay characteristics, several factors must be taken into account. Firstly, the rated current of the breaker must match or exceed the continuous load current of the circuit it protects. Secondly, the interrupting rating of the breaker, which is the maximum fault current it can safely interrupt, must be higher than the available fault current at the installation location. Thirdly, the time current curve of the breaker must be compatible with the protected equipment and the overall protection scheme. The time current curve illustrates the relationship between the magnitude of the overcurrent and the time it takes for the breaker to trip. By comparing the breaker's time current curve with the equipment's withstand curve, engineers can ensure that the breaker will trip before the equipment is damaged. Coordinated protection is also a crucial consideration. This involves selecting breakers with time current curves that are coordinated with upstream and downstream protective devices. The goal is to ensure that the breaker closest to the fault trips first, minimizing the impact of the fault on the rest of the system. In addition to the manufacturers already mentioned, other companies may offer 2-pole 60-amp, 230-volt breakers with time delay features. It's always a good idea to research the available options and compare their specifications before making a decision. Consider the specific requirements of the application, the available fault current, and the desired level of coordination. Consulting with an electrical professional is highly recommended. They can assess the installation conditions, perform calculations, and recommend the most suitable breaker for the job. Remember that electrical work can be dangerous, and it's essential to follow all applicable codes and safety regulations. Always de-energize the circuit before working on any electrical equipment, and use appropriate personal protective equipment. Circuit breakers are not a one-size-fits-all solution. The best breaker for a particular application will depend on a variety of factors, including the type of load being protected, the available fault current, and the desired level of coordination. Take the time to carefully evaluate the options and choose a breaker that meets the specific needs of the application. Before installing any electrical equipment, it is vital to consult with local electrical codes and regulations. They ensure safe and compliant installations. Many municipalities follow the National Electrical Code, or NEC. However, local amendments may exist, so it is imperative to verify the requirements in your specific area. The NEC provides comprehensive guidelines for electrical installations, covering topics such as wiring methods, overcurrent protection, grounding, and equipment installation. Adherence to these guidelines is essential for ensuring the safety and reliability of electrical systems. When selecting and installing circuit breakers, several NEC articles are particularly relevant. NEC Article 240 addresses overcurrent protection, including the selection and coordination of circuit breakers. It specifies the requirements for breaker ratings, interrupting ratings, and time current characteristics. NEC Article 430 covers motor circuits, which often require special considerations for overcurrent protection due to the high inrush currents associated with motor starting. It provides guidelines for selecting breakers with appropriate time delay characteristics to prevent nuisance tripping. NEC Article 408 addresses switchboards and panel boards, which are common locations for circuit breaker installations. It specifies the requirements for the construction, installation, and labeling of these assemblies. In addition to the NEC, other standards and guidelines may be applicable depending on the specific application. For example, Underwriters Laboratories, or UL, standards provide requirements for the safety and performance of electrical equipment, including circuit breakers. Compliance with UL standards indicates that a product has been tested and certified to meet certain safety requirements. The Institute of Electrical and Electronics Engineers, or IEE, develops standards and guidelines for various aspects of electrical engineering, including power system protection. IEE standards can provide valuable guidance on the selection and coordination of protective devices, such as circuit breakers. When working with electrical systems, safety should always be the top priority. Electrical hazards can cause serious injuries or even death, so it's essential to take precautions to protect yourself and others. Always energize the circuit before working on any electrical equipment. This involves turning off the breaker or switch that supplies power to the circuit and verifying that the circuit is de-energized using a voltage tester. Use appropriate personal protective equipment, or PPE, such as insulated gloves, safety glasses, and arc flash-rated clothing. These items can help protect you from electrical shock, burns, and other hazards. Follow safe work practices, such as maintaining a safe distance from energized equipment, using insulated tools, and avoiding contact with water or other conductive materials. If you are not qualified to perform electrical work, do not attempt it. Hire a licensed electrician to handle any electrical tasks that you are not comfortable with. Proper grounding is a critical aspect of electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the breaker and clear the fault. Ensure that all electrical equipment is properly grounded in accordance with the NEC and other applicable standards. Grounding systems should be regularly inspected and tested to verify their effectiveness. Arc flash is a dangerous phenomenon that can occur when a short circuit creates an electrical arc. Arc flashes can generate intense heat and pressure, causing severe burns and other injuries. To protect against arc flash hazards, it's essential to conduct an arc flash hazard assessment and implement appropriate safety measures. This may include wearing arc flash-rated clothing, using arc flash barriers, and following safe work practices. Regular maintenance is essential for ensuring the reliable operation of circuit breakers. Breakers should be inspected periodically for signs of wear, damage, or corrosion. They should also be tested to verify their proper operation. Testing may involve using a breaker test set to measure the tripping time and current of the breaker. If a breaker fails a test or shows signs of damage, it should be replaced immediately. Circuit breaker technology is constantly evolving. Manufacturers are continually developing new and improved breakers with enhanced features and capabilities. Some of the recent advancements in circuit breaker technology include arc fault circuit interrupters, or RFIs, which are designed to protect against arc faults, a common cause of electrical fires. Ground fault circuit interrupters, or GFCIs, which are designed to protect against ground faults, which can cause electrical shock. Smart breakers, which incorporate communication and control features, allowing them to be remotely monitored and controlled. Solid-state breakers, which use electronic components instead of mechanical parts, offering faster tripping times and improved reliability. When selecting circuit breakers, it's essential to stay up to date on the latest technology and choose breakers that meet the specific needs of the application. Remember that circuit breakers are a critical component of any electrical system. They provide essential protection against overcurrents and short circuits, safeguarding equipment and preventing electrical hazards. By carefully selecting, installing, and maintaining circuit breakers, you can help ensure the safety and reliability of your electrical system. In summary, selecting a 2-pole 60-amp, 230-volt breaker with time delay characteristics involves identifying appropriate manufacturers like Siemens, Eaton, Schneider Electric, GE, and Square D. It requires careful consideration of the breaker's time current curve, ensuring it aligns with the protected equipment's needs and facilitates coordination with other protective devices. Consulting with an electrical professional is crucial to ensure proper selection and compliance with all applicable codes and safety standards.